Yeah, so I'm Adrian Gheorghe. I work for Stefanini right now. And one of the cool things that I do is that I organize front-end meetup. I'm one of the organizers. The rest of them are in the room as well. I'm one of the organizers of front-end meetup Bucharest, a local conference about JavaScript front-end in general, actually. I go online as DVS Dodo, usually, and my email is on the screen. So if you need to contact me afterwards, just fire up an email or something like that. Cool. The talk is going to be about functional programming and how we can use functions to construct programs. So let's get to it. First of all, a bit of a definition. What is functional programming? There are many things that are mentioned when people talk about functional programming, like high-order functions, like no side effects, and many other things. But the core idea is actually it's found in the name. It's just application of arguments to functions. But the core idea is that functional programming treats computation as the evaluation of mathematical functions. And of course, it tries to avoid change state and mutable data. But what's the idea behind mathematical functions? Mathematical functions are pure functions, and pure functions have a couple of interesting properties. They can have no observable side effect when they're executed. We'll see in a moment what kind of side effects we can have in a language, in a function. And the other very interesting property of a pure function is that it returns the same value for the same input if you call it multiple times, which is a very strong guarantee. Some examples of pure functions. As you can see, the functions only depend. By the way, can you guys see what it says there? Yeah, I hope it will fit. Just a second. Nope. Unfortunately, it doesn't seem to work.
Try reducing the resolution. Resolution smaller, it will make the image bigger.
Okay. Okay. Let's see how that works. I don't have any options for that. Nope. Nope. Sorry. Okay, that's gonna be a bit of an issue. I don't know what to do about that. Hmm? Okay, so yeah, is it possible to do anything? No. Okay. Yeah, so these are just some examples of pure functions. They're very simple functions. We have a function square, which takes a number and computes the square of that number. And we have another function, which is check age. It just receives a number and returns a Boolean saying whether the number is greater than 18 or not. I don't see anything on my screen, but that's fine. OK. Is it a bit better? OK. Cool. Some of the advantages of pure functions. They're self-contained. They're self-documenting. They receive all the arguments they receive all they need, all the other functions they need, or all the data they need as arguments. They don't look outside of their scope. This makes them very easy to test. They don't have any other dependencies, so you just pass in whatever you need. They're also very portable, so you can just copy and paste them to another project. They have a very interesting property called referential transparency. We're going to look at an example of that in just a moment. And another cool thing about pure functions is that they're very concurrent, in the sense that it doesn't matter when you execute them. So if you have a set of functions that the compiler needs to run, they can be distributed over multiple cores, because they don't care about anything else that happened before, or they don't care about any of the state that's present in the program at that time. So they can be executed separately, concurrently. Referential transparency means that we can actually replace the function call with the value once we compute it. So we can think of a function simply as a map of the inputs to the values that have been computed. So for example, if we consider our square function, we can define it as a function. And if we apply 3 to it, it will return 9, obviously. But we can also replace that with a map of all the values that have been called so far, of all the inputs. And the values would, the keys would be the inputs, and the values would be the computation result. And in this case, we can simply do a hash map lookup to replace the square 3. Does that make sense? OK, so what are side effects? We have a lot of possible side effects that can occur in a program. Most of us think of them or try to avoid global state, and that's bad. Another possible side effect that a function can have, it can mutate its arguments. So for example, if we pass an object or an array and we change it within the function, that's going to be an observable side effect. The function can also raise exceptions that will change how the program runs, given different inputs. Other very useful side effects would be like interacting with files, with database, with the DOM, for example. That's a side effect. Anything that reads or writes data to the outside, to or from the outside world, is a side effect. Okay? That's unfortunately almost everything that's useful for a program. The problem with the side effects and with functions that use side effects is that they're not self-contained. And understanding a function, looking at a function that has side effects, in order to understand it, you need to look at the context in which the function has been defined, because it uses some data from the outside world. And at the same time, running the same function twice will not guarantee the same output. Why? Because the function will use some external data. That external data may have been modified somewhere else. As an example, it's still visible? OK. We have, again, defined, I've given 2 examples of impure functions. Check age, for example, in this case, reads the age variable from the outside world, which makes it impure. And another function that's more interesting is make request. Make request simply makes an AJAX request. right? That's impure because it executes an I/O call, and that call can fail, or it can have different results each time you call it, which obviously is impure. The key idea from this, and this is where actually things start to get interesting, is that you can transform certain functions that are impure, in particular functions that do I/O, for example. You can transform them into pure functions. How? You make the function return another function. So for example, we have a pure request function in this case, which takes a URL, but instead of performing the AJAX call, it will return a new function that will perform the AJAX call when it's called. So this seems like there's no difference in the sense that we still have to perform, we still have to call the second function in order to get the side effect, and that's true. But that's the responsibility of the caller. The function itself is pure in the sense that for each input that you call it, it will return the same thing each time. It will return the same function with the same structure that will make the same request. Just the request itself, that's the impure part. And we don't care about it because we have abstracted it in a function call. We'll see how this is very useful a bit later in the second part of the presentation. But just remember that we can transform impure functions that do I/O into pure functions by simply putting by simply returning or wrapping the I/O call in another function. Okay, one last thing, and then we're gonna move over to looking at some code. One last thing I want to say about functional programming is that it's considered a declarative programming paradigm, in the sense that computation, we just declare our intention. The computation itself is represented by expressions that describe what we want to do. It's not imperative, where in imperative programs, we use state and change that state in order to achieve the effects that we want. For example, the code is visible. I have a list of numbers, and there are two ways to compute a new array of the squares of the numbers. The first one is imperative. It simply does a for loop, and for each number, it creates it modifies a new array, a result array, to put the operation there. The declarative version uses map to apply a function to each of the elements. How many people know what map does? Okay, cool. Just want to make sure. But there is one interesting thing about this map function that you see here. It's not applied on the array itself. It's just a map function that receives a function, and as the second argument, it receives a callable or a mappable object. This is not native to JavaScript. It's implemented in some libraries. The functions that I'm going to use, and there are a few more, are from Lambda. And they're a bit different if you're using underscore or Lodash, because there you will see the function as the last argument. In Lambda, you get the function as the first argument. And that's pretty neat, and we'll see soon why. One other thing that's interesting is that people, when they look at the declarative version, think, OK, map, but that's implemented with fors. You still have to do side effects, or you still have to do imperative programming at some point. That's not true. Map can be implemented with a for, obviously. The interface is not really important, but the thing is that we can still implement it without using imperative programming. We can implement it using recursion. And this version is very simple. It's simpler, it's shorter and simpler logically than the imperative version, in the sense that it simply concatenates the result of applying the function to the first element of the array with the result of applying the function to the rest of the array. By the way, I will have a link at the end of the talk, or I will send an email or something like that with the code, so you will be able to see it online if it's not visible. Right. So, probably the biggest advantage that functional programming has, or the biggest advantage that it brings, is modularity, and that is related to how functions, how we can reuse functions, and we can create new functions very easily to abstract functionality, to reuse functionality. Currying, for example, how many people know what currying is, to know how much time I should spend on it? Okay, I'm going to explain then. About half, by the way. Okay, so what is currying? Let's say that we have a function that has more than one argument, 2 or 3 arguments, and if we call it with fewer arguments than it has, we will get back a new function that expects the rest of the arguments, right? Let's see an example. This is without currying, right? So we have a filter function. Is it okay? Okay, I'm going to explain generally what it does. I cannot read the code, but I can explain what it does. So I have a filter function, which simply applies filter to an array. And I have a predicate function, is even, right? And in my program, I want to create a new function that will just filter all the even numbers in the array. It's very easy. I can create a new function, right? Filter even, that takes an array and then calls a filter with the isEven predicate and with the array itself. The thing here is that in order to create a new function, I actually had to write a new function by hand instead of being able to reuse the 2 functions that I already have. Let's see how we can do it if we add currying to the mix. So instead of defining filter as a simple function, I wrapped the function definition in a curry call. This curry function is also implemented by Ramda. And what it does, if we call the function with the 2 arguments that it expects, it will simply call the function. But if we call it with only 1 argument, it will return a function, a new function, that expects the 2nd argument. Okay? What this means is that we can define filter even as simply calling filter with only 1 argument, with the predicate. This will get us a new function that expects an array, and we have the same functionality without writing any new code. This is, if we had tested filter and isEven, we don't have to test anything else. The function works simply by definition. Okay? Is this clear with the currying? Does anyone? By the way, if you have questions, and if you can read what it says, you can ask. You can raise the hand and ask anything at any time. Okay, another tool that we can use with functions, another thing that we can do with functions is function composition. This allows us to create more complicated functions from simple functions. The result, let's see an example, right? Let's say I have a function square, which computes the square of a number, obviously, and we have a function inc, which increments a number. If we call compose over these 2 functions, we will get a function that performs the computation specified in right to left order. So our increment square function will actually square the number and then increment it. So the result of each function is passed as the argument of the next one, from right to left. Okay? It's a very simple concept, but it's very powerful. Again, compose is defined by Ramda. These are all built with plain JavaScript. It's not difficult to implement them, but Ramda is quite neat. You can have a look at it. Okay, let's take a more complicated example to show off both currying and composition working together, right? The boss comes and he says that he wants a function that will receive an array of strings and that will return a slug. What is a slug? It's the URL. It's the last part of a URL for articles or whatever objects we have saved in the database. Yeah, but don't hold me on that definition. Anyway, so we have an array of strings, and we want to calculate the slug. We define a slug as simply being lowercasing the items and just keeping the letters, removing numbers and any other signs of punctuation from the strings themselves, right? Our initial function slug, it receives an array, and then what it does, and you have to read from right to left. Initially, it applies downcase to the words to make them lowercase. Then it applies keep letters to the result, right, to remove any signs of punctuation, and then it joins the array, right? We see a couple of things here. Map is curried in the sense that it only receives the function, but the main thing here is that the function is a bit weird. There are many nested parameters there, right? So let's improve it a bit using compose. The old definition is commented out, and I've written below the compose, the same function, but using compose. It's quite a bit simpler and easier to reason about, right? It's just a composition of the functions downcase, keep letters, and join. And it does exactly that. It's very easy to read it. The only problem that we have with this function right now is that it maps twice over the array, right? This is not efficient. We map once to downcase, and we map again to remove all the punctuation. What can we do to improve the situation? Well, we could compose the two functions that are actually mapping over the array. And the third version is, again, much simpler, and it's also much more efficient. So we define a new function, downcase letter, which is just a composition of the keep letters and downcase. And slug becomes a composition of join and downcase letters. It's quite expressive and quite short. Questions so far? OK. By the way, I'm going to mention this again later. There are some things that I'm glossing over, like, for example, slug. I mean, the way slug is defined is called point free. Okay. A point free, by the way, means that you don't have to specify the arguments. OK, so at this moment, we have some tools that allow us to pipe data through through pure functions, right? So we have some tools that allow us to compose functions. We can query them. Everything works great. Unfortunately, the problem is with the real world. That's always the problem. So what we do if we need to interact with I/O, if we have asynchronous actions, or if we want to implement better control flow for the functions. Well, before I get to the next part, I'm just going to say that there will be many things I'm going to gloss over. Many things. The functors, applicative functors and monads that I'm going to talk about are they come from category theory, which is a very abstract branch of mathematics. So I'm just going to try to give you an intuition of how they can be used. But the formalisms are quite a bit more complex. and I'm not going to mention a lot of things. But I hope that you will understand at least how they can be used. Okay? So, the first thing that we're going to discuss about is a functor. There is a bit of overlap over what a functor is across different paradigms. For example, in C++, it's just a pointer function, or it's a class that it can be called as a function. But what we care is the definition of the programming world, or the functional programming world, where a functor simply represents a kind of a container, right? We will see a bit later a better abstraction, but for now we can consider it a container that holds a value. And this container allows you to apply a function to the value that it contains, right? Let's look at a very simple implementation, okay? It looks like an interface or a type, right, that implements a map. So we could call it mappable, for example, right? But let's call it functor, because it's cooler. And as you can see, we have a constructor that stores the value, and we have a map that allows us to apply the function. But the key value here is that the map function actually returns a new container. It doesn't return a value in itself, it returns a new container, right? So at the end, I have, I'm logging something to the output. We have new container of 2, map square. Square, obviously, square is the number. What do you think will be the output of that function? It's not 4, it's a container of 4. And this may not seem like it's a very big deal, but it's actually very powerful and very important. One thing that we get from returning a new container, right, from the mapping function, is that we can chain map calls, right? For example, we can map the square over 2, and then we can map again an increment function that will output 5. The very interesting thing here is that we already know some data structures that implement map. Arrays, right? Lists in general, but arrays in our case. Arrays are just an interface that implements map. And in fact, there are a functor in themselves, right? So lists are a functor, but we're going to focus on a different aspect of functors right now, rather than having multiple elements. And the key here is the last 2 lines. The fact that having a map function as an interface allows us to reuse the generic map that Lambda provides, right? So we can apply functions to functors as we would apply functions to arrays, for example, right? So we have an object, and we can apply any function to it. The thing is, it still seems complicated. I mean, why would we do this? Why would we just store values to apply functions to them through another function, right? What do we get from putting values in a container and using map to get to them? The better question here is what do we get from asking our container to run functions for us, right? So the key is that the container will run the functions. And that allows us to abstract over a function application, right? What this means is that the container actually defines the context, right? Our previous map function didn't do anything, it just called the function. But we can embed logic within that map function, right? We can create a container that applies the function only if the number is odd, for example, or only if the number is even, right? So we can embed some logic in that map function, and allow the container to call it however it wants or whenever it wants. Okay? And so far we said that functors are something like a container. You can think of the containers or the functors as being sort of a computational context, right? There is a bit of computation going on there, and the container will allow us to insert the function within that computation. Okay. Let's look at this will allow us to express higher order concepts, but let's look at another example of a functor, which has a bit more structure, and which actually has some benefits. We have the functor called maybe, which is probably the first thing that you will read about if you read any tutorials on functors or monads or anything like that. The maybe functor does only one thing. You create maybe you create a functor from a value, and if the value is null, right, when we map over it, it will not apply the function, right? It will just return a new empty container. If the value is different from null or undefined, so if the value is not nothing, it will apply the function to the value and return a new container with that value. Okay? So let's look at a few examples. The first one creates maybe hello world and maps lowercase to it. This will simply return a new container, a new maybe, with the function applied to the value. So it will be the same string but downcased. What happens if we apply to lowercase to a null value? We will get an error if we use it, if we do it in JavaScript directly, but if we use this functor, we will return, no error will happen, and we will return back a new empty container. What we have here is just a null check. So we implemented a computation within the data structure, right? This allows us to perform functions in case we fear that a failure might occur, or we have some invalid data. Let's look at another example. We have a save head function. If we have an array, the head function returns the first value of the array. Unfortunately, if the array is empty, what will the head function return? It will return undefined. And if we try to apply a function to that, we will get an error. But if we define a save head function, as here, it will return a maybe of the first element of the array, which allows us to apply other functions to the value without worrying whether the array is empty or not. If the array is not empty, everything will work. Otherwise, we'll get back the same empty container. Okay. This works fine, right, for functions with a single argument. Okay. So if we have functions with a single argument, we can use functors, and we can apply. We can map those functions over the functor. But what happens if we have functions with multiple arguments? A very simple example is add. Add needs 2 numbers, right? We need 2 parameters to get a sum. We can do that with one of the values being a functor, using maybe, for example, and we can apply a function. We can apply 3 to it. But what happens if we want to add 2 containers together, right? Things will not work. You cannot add a number to a functor. Is this clear? Okay. We need the function. The core idea here is that we need a function that can apply functors to each other. what this means is that if we have a functor that has a value of a function as a value, we would like to apply another function to it, another functor to it that contains a value, and we will return the computation result. This is what applicative functors are. They're simply functors that allow us to apply functions wrapped in containers to values wrapped in containers, right? Maybe, again, we define an app function, and what it does, it simply calls map on the other container that it receives with this value. Remember that this container that we're using stores a function, right? So this value is a function. And the other container that we are receiving contains a value. So we are applying the function contained here to the value. Okay? This allows us to use something like the code below, where it starts to look like normal programming. You can do maybe of 2, map add, and you can then apply another functor to it, maybe of 3. And the last thing, the last part that we are going to look at is something that I showed on the first slide. What if we have functions that take normal values, right, and return containers? Our safehead function was an example of that. It simply returned the first element of an array wrapped in a maybe. But if we have another function that does the same thing, returns another container, and we want to compose these two functions together, we will get 2 containers embedded in each other, right? First square of 2 numbers will return maybe of 4. First square of an empty list will return maybe of null. So what we need, of course, we would simply want maybe without the nesting. It's useless in that case. What we need is a function that can apply. We need a function on the functor definition. We need a function that can apply functions which return containers to other containers. This is what monads are. The example will be very simple. Monads simply apply a function that returns a value wrapped in a container to another container. The definition is difficult, but let's look at an example. If we see the chain function, this is what defines a monad. The chain function simply calls f and then calls join, if you see. What does join do? Join is just a helper. Join will simply flatten 2 functors together. So if we have maybe of 4, join will simply return maybe of 4, right? Which leads to, again, very easy to read code at the end. So we can use functions that return functors, and we can compose them using chain. Right, those were the definitions. Actually, how much time do I have? Okay. So the functors, the core idea that you have to understand is that functors, applicative functors, and monads are just containers, and they define some laws by which some functions are applied to the values inside them. This allows for some powerful abstractions. They can be used to model state asynchronous functions, etc., etc. For example, for I/O, and this is the last slide. For I/O, we can think of map as simply returning, right, a new functor with the value wrapped in a function. So, for example, if we have, if we want to read a file, we will not read the file directly. We will use what I showed earlier in the sense that we can delay the computation by wrapping it in a function, right? So I/O simply allows delaying the input-output. One last thing that I would like to mention is that, for example, we already have other APIs that can be used as functors. Promises, for example, right? Promises that we use every day, they model asynchronous computation. The problem with promises is that they're not pure. Why is that? When you create a new promise, right, you pass it a function, and that function will be executed immediately, right? It will take some time to be resolved, but the function will be executed immediately. That's impure. We can make a very small change to how the promise spec works, and we could, for example, not call the function immediately, but wrap it in another function call, and that would make them pure. And there are some libraries that actually implement most of the useful functors and monads and everything else that are available in other languages. They're Folktale and Fantasyland. I'm going to provide some links afterwards. And if you are interested in seeing the complicated part with the algebra behind the concepts that I explained here, you can look there. And that's it.